Good afternoon, this is Schweitzer, and I'm going to do a quick calculation here on how would you calculate a K value. Now again, why is a K value important? A K value is giving us a relationship between the concentration of the products over the concentration of the reactants, and this is a great way to tell us the concentration of any item at equilibrium. Which is our main goal of any equilibrium concentration is to figure out what is the concentration of an item when the reaction comes to an end. In this case, the K really is just a tool we use to get this. The K by itself means nothing. It just tells us to what extent the reaction proceeds. We have a concentration of reactants, we have a concentration of products, and K is usually, so when this reaction comes to a balance of both forward and reverse reactions, where are we on this thing? Are we over on the reactant side, or are we over on the product side? Or technically, maybe it would balance right in the middle, where you would have equal amount of products and reactants. Okay, so let's just try an example. Now again, I'm going to use a similar example of Ag2SO4, and the very first thing I do, come across an equilibrium problem, is I write out what is the equation that's happening. Comes from Ag plus SO4 minus 2. And this will be a 2 here and a 1 here. And I usually leave this out here just as an opportunity for me to be able to put information in as I come along. I might be reading through my problem as I'm going, and I now write this out, and I'm continuing to read the problem. My KSP equals the concentration of my Ag plus squared times the concentration of the SO4 minus 2. Alright, at this point, you read through the problem, you realize that they want you to calculate the K value. Now, KSP for this guy, right here. Anytime they want you to find a KSP value, or any K value, you need to have all the concentrations at equilibrium. Now this guy, there's no reactant, but we'll eventually get to situations where there are reactants. So you simply need to have all this value, you need to have this value, and if there were any reactants that weren't solids, you would need those too. So you need everything that's on the equilibrium line. You simply plug all those guys right there from the equilibrium line, and you plug them into this expression. And you just complete the expression and find KSP. But in this case, if they want you to calculate KSP, they usually got to give you something. Okay? And what they're going to say, okay, they'll say, okay, well, at equilibrium, the concentration of the SO4 minus 2 is found to equal 0.0135 moles per liter. Determine K. So, pretty standard problem. Again, we're dissolving silver sulfate. So, you draw a picture of this guy, and you should note that every time you dissolve one silver sulfate, you get 2 silvers and 1 sulfate. So the concentration of your Ag pluses is always going to be twice that of your sulfate. So if your Ag plus ion concentration is unknown, your sulfate ion is equaling 0.0135. It's double for that guy, because I'm dissolving silver sulfate, which stoichiometrically has 2 of these for every 1 of these. I could take the silver from one source and the sulfate from a different source, and then they wouldn't be locked by a chemical formula. They could have 2 separate, totally independent formulas. But in this case, because we're dissolving this item, then that locks these 2 concentrations at a 1:2 ratio. And therefore, this guy is 0.027. Again, it's only reason why it's a 1-to-2 ratio because I'm dissolving this item. So at this point, I have both my concentrations. You'll note that it'll say at equilibrium, the sulfate ion concentration is this. So I immediately just take this and go 0.0135. Anytime they give you an equilibrium concentration, go ahead and just drop it into the formula. Next, we want the silver. This is going to be 0.0271. All right, there is nothing for the solid, so plug it into your expression, and let's do this. We have 0.0271. Again, by our formula, this guy gets squared. Even you doubled it and you squared it in this situation. And the sulfate is 0.0135. And from that point on, it's simply calculator work. .00271 squared is 0.000471, so 0.0000471 times 0.0135 gives me essentially 6.0 e to the negative sixth. Okay, now I select the molarity on there, but really there's no molarity. This is a K value, and it is not involving a unit. The units change all the time here, and technically it'd be molarity cubed times molarity. It'd be molarity cubed, but we don't generally include this as having a unit. This would be my K value at this point. Okay. This K value, does it always have to be the same? Well, let's see. K values are temperature dependent. All right, so as soon as you alter temperature, you alter the K. That's pretty much the only time the K would change. We did a problem earlier on this problem, and it was 1.0 e to the negative fifth. I used the same numbers, but with rounding, we got a slight variation, which is fine. The process is more important than the little bit of rounding differences. Other than that, this is a pretty common problem. They want you to find a K value. Given a K value, they gave one of the concentrations was given, and off of that one you could figure the other one out, and then plug it into your expression, and you could solve for your K value. Pretty common problem.